All right, thank you very much. Very excited to be here. Only have 30 minutes, so I'm gonna have to go fast. I mean, not too fast. So the goal of today is to understand a bit better how VPA, HPA, KEDA works. I'm not gonna talk too much about nodes. Actually, I'm not gonna talk about cluster autoscaler. But I mean, basically for nodes, you have cluster autoscaler, Carpenter. Use Carpenter, it's better. Job done, all right? So it will also be based on a demo, like a Rube Goldberg machine, and the goal is going to be to break my application. But before that, I'm going to have to be able to understand what's going on, I'm going to have to talk about requests, limits, quality of service, priority class. So who is familiar a little bit with that already? Some of you? Okay. It's kind of confusing, so I'm going to use a couple of metaphor and images to be able to explain that. Let's aim for maybe 10, 15 minutes, and then we'll try to break the application where we'll see everything in action. So my name is Nick. I've been doing Kubernetes stuff for probably the last 8 years around CNI, CSI, edge security. Usually I'm either in DevRel, engineering, or product management. I've been in this industry for 25 years, getting old, but yeah, it's just experience, right? Yeah, I enjoy coding fun apps, usually like Rube Goldberg machine, overkill application. This is my thing, I love to do that. I'm also an avid distance runner, and probably the best way to connect with me is either LinkedIn, but probably Strava, where I'm probably the most active. All right, so why do we need to do autoscaling? Well, because simply, a lot of resources are wasted in the cloud, so it makes sense not only to scale up, but to be able to scale down, and having a good, good idea of what is running in our cluster. But at the same time, we have to right-size everything, and to have, elasticity is probably one of the most important aspects. So according to one report from Akamai 2017, like 100 millisecond delay is 1% decrease in sales, right? So we have to make sure that our infrastructure can handle performance application. But unfortunately, HPA, VPA, KEDA, autoscaling, there's a lot of notion to be explained there, and there's a lot of knobs. So like Homer, you can be very confused because of all these knobs. So there's a metaphor I like to take, is a kitchen metaphor, to be able to make distinction between VPA, HPA, and KEDA. So let's start with the kitchen, right? So the kitchen is basically our cluster. So we're not going to scale the kitchen today. And then we have the orders. Orders will be our containers, and the orders are made of ingredients. And ingredients are themselves resources, or the metrics associated with the resources. And our scalers the pod is essentially the chef, right? Or a group of chefs. And this is the resource that we need to scale. So if we make this comparison, we can first talk about VPA, so vertical scaling, which is essentially you have, for one particular chef, you give it much more power. It can do a lot of things with the ingredients. It has more tools, and the idea inside Kubernetes for the VPA is to recommend requests for your workloads, right? So typically you start with VPA just at least to have an idea for profiling your application. This is the basis to profile your application. Then you can of course enforce those requests, which we're going to see later. And then we have HPA. So HPA is kind of, by default, quite dumb. The ingredients are exactly the same, typically CPU memory, and you just scales based on that, right? So it's not super intelligent. You can customize it. We're going to see how to do it, but if you really want to customize HPA, then there is the smart guy, right, which is much more lean. KEDA is acting as a chef, as a proxy, so you have the chef of all the chefs. And KEDA will give you those special ingredients, or different kitchen. Maybe you're gonna eat, you're in London, so probably it's a good idea to eat Indian here. So it's acting as a proxy on top of HPA to have specialized chefs, right? So essentially, it's making HPA much more intelligent. We're gonna see this in detail. But before going into those details, we have to understand the notion of requests, limits, and quality of service. Essentially, mainly requests, because request is going to be the special metric that is going to be used by all the scalers. So if you say the trigger is going to be 50% or 60% of my resources to scale, this is going to be based on the requests, which means that request typically needs to be as much as possible as close as the profile of your application. So if your application is consuming 100 millicore of a CPU, that needs to be the value as an average. Same for memory. You have to know your application, how it's behaving. And then, of course, the request itself guarantee, it's the amount of resource guarantee in case of contention. So it's really the minimum. And it's also informed the scheduler for placement decisions. So if the request you want to allocate to a pod is not available on the host, then the host is that particular node is not going to be considered for placement. So it's also very important. So if it's too low, well, pods might be scheduled on stray nodes, which is not good. If it's too high, you can waste a lot of resources. And as I said, the good practice, the request should be aligned closely with the actual usage. And as I said in the beginning, you can start just using VPA just to profile your application. So limits, it's the resource boundary. It has a couple of effects. So usually you can, if you look at Reddit or some documentation, it's not necessarily recommended to apply limit on CPU, just because if you apply limit on CPU and you go above that, you will have CPU throttling. As opposed to if you don't put any limits and if the node doesn't have enough cycle, then your pod, the task in the pod, is going to be scheduled less on that CPU. And there's quite often a confusion. If it's scheduled less, it doesn't mean it's throttle, right? These are two different things. So remember, limit equals CPU throttling. If you don't put any limit and there is a contention for CPU, it just means that the task or the pod is going to be scheduled less often. And of course, memory limits, this one is quite bad because, if the pod goes above that limit, whether there's contention or not, then it's going to be OM killed by the kernel, right? Okay, now quality of service is determined by those two resources. There are three classes: guaranteed, burstable, and best effort. And these three classes determine the eviction priority under resource pressure. So a node resource pressure, the typical two ones, there's no pressure, there's no such thing as node pressure for CPU. Maybe for PIDs, but not for CPU. Typically, you will experience node pressure for disk and node pressure for memory. Those are the main two conditions. But here, remember, guarantee, burstable, and best effort, which is the metrics that is going to be considered, are related to request and limits for CPU and memory, right? So those are kind of disjoint, right? So guarantee is deemed for pods where requests equal limits, and that will be the last considered to be for eviction, with the little kind of tricks where if you only put limits on a pod without any interaction with other webhooks or admission controllers, if nothing is modified, then so Kubernetes is going to copy the value of the limit into the request. So basically, if you only set limits for pods, you're going to end up with guaranteed workloads because it's going to copy the value of the limit into the request. Therefore, they are equal. For other scenario where, actually it's the opposite. I just realized so limits is superior to request and not request superior to limits. Those are deemed burstable. So typically, this is most of the time what you're going to end up with. And there's also other scenario. For example, if you omit one request for CPU and only have memory, then it's going to be burstable. It's basically everything else, except when nothing is defined. In that case, it's going to be best effort, right? So I think I will have a table later. With that particular gotcha that's if you apply CPU limits, like I said before, CPU throttle can happen. Therefore, if you define a trigger that is too close, so if you say request equal limits, remember what I said at the beginning, then it's a percentage not of what is used by the pod, it's a percentage of the request, right? So if the percentage for the trigger, let's say 90%, is too close to the limit, and if limit for CPU equal request, it means that probably the CPU will be throttled before the triggers happen, right? So there's a kind of gotcha here, so be sure that when you want to monitor for CPU scaling, put the trigger not that high so that CPU is not throttled, or just don't put any limit on the CPU. But again, if you don't put limit on the CPU, your workloads move from guaranteed to burstable, right? Which is then again, in terms of eviction, a priority may change. All right, so these are three, I need to go fast. So three scenarios. Requests, we have a use case here, 100 mil CPU, 200 mil memory, or not defined at all. In that case, if we also have limit defined, Kubernetes is going to copy the limit into the request, if the request is not defined. Or if they are equal, it's guaranteed. So this is falling into that particular area. Then for basically anything else, so when you are missing one request for CPU or memory or limits, or a mix of requests being inferior to limits, so basically not equal, it will be burstable. So anything that is not equal, where CPU and memory limits equal request, anything that is not that will fall into burstable, and the rest, meaning that nothing is defined at all, is going to be best effort, which you really want to avoid because they are considered first to be evicted. I'm not going to talk too much about priority class here, but just be aware that there is a completely orthogonal mechanism, which is priority class, that is only evaluated for scheduling, that can also preempt, which means that it can evict pods if you do it. I mean, don't necessarily enable that option, so you can just say, don't evict pod, just use priority class at scheduling without evicting. And the priority class, you can think about it once the scheduler is going to consider, once kubelet is going to consider the different quality of service for eviction, so first, best effort, burstable, guaranteed, you can establish order within those quality of service by using priority class. So the recommendation here, without going too much into details, if you have workloads you manage with HPA or VPA, therefore probably going into the burstable, if you don't want to set the limit on the CPU, right, it's going to be burstable. Always make sure that you have a priority class that is high for those workloads, right? Okay, so VPA. I'm just showing here some configuration. Essentially, it has three modes, initial, off, or auto. Initial is great is going to generate recommendation, but not doing anything else. So more like for profiling. Off, which just run into dry mode. Auto recreate, then you can have, this is where it's going to restart the pods to apply requests and limits because you have to restart the pods to do it. You cannot do it live, right? So if it's a stateful set, you have to have extra care, and of course you can also plan for a pod disruption budget, which is guaranteeing a minimum of pods for a particular workload, which is the recommendation. If you're using VPA, essentially make sure to go initial, or if you want auto, make sure to have PDB configured. Then you can monitor memory or CPU. Typically, you want HPA working on CPU because CPU is actually representing a value that will have a direct impact on the number of pods rather than memory. Memory is like a watermark, so it's more difficult to use HPA for that. So the idea, use memory for VPA and use CPU for HPA. It's not, I would say, most of the time it's going to be that, but depending on your environment and the type of workloads, it can be other things. But usually, memory, VPA, CPU, HPA. So three main components, the recommender that is going to monitor the resource usage metrics, either using kubelet and cAdvisor, or the metric server, if it's available, and store the recommendation in the custom resource, which we're going to see. The updater's job is just to evict the pod. It's only active in the auto mode. And of course, as I said, if you have PDB, which is best, it's going to respect PDB. And then the admission controller, it's basically using a webhook to intercept the pod at creation time and modify on the fly the request for CPU and memory if you control both. Okay, so this is whatever, I mean, I've also already mentioned all of that. The only thing I didn't mention is configure max allowed, which is basically telling VPA never go above that particular threshold. For HPA, so you give essentially a minimum number of replica, maximum number of replica, and then again, average utilization in percentage in that particular example for CPU, but remember, it's not percentage of memory used, or CPU used, sorry, it's the percentage of the requests that you have defined for that particular workload, right? There's a big difference in this. How does it work? So we say number of desired replica is just basically number of currents times the current metric value divided by the desired metric value. So here I just have an example. If you have currently 90% CPU use, I mean from your request, 50% desired target, one replica, it's 1 times 90 divided by 50. Ceiling of that is 2, so it's going to move to 2 replicas, right? So it's a constant formula. So for HPA to work, you need the metrics server to be there. And you can also implement custom metrics through Prometheus adapter, but you have to do it yourself, right? And register that to the custom metrics API endpoint. But if you're smart and don't want to work for nothing, if you really need to do that, just use KEDA, right? So essentially, HPA use metric server, which is installed in 2 minutes. And HPA is, by the way, it's already there inside Kubernetes. You don't need like a special operator, right? But if you want to do smarter things than CPU and memory, use KEDA. And HPA cannot scale to 0. KEDA will give you that particular capability to scale to 0. And KEDA is going to automate the creation of HPA, implementing external metrics. So KEDA, instead of having Prometheus adapter register on the external metrics, is going to use its own object, which is called a scalar, and that particular scalar, which represents a set of metrics, is going to be available on this particular external API endpoint, and then HPA can just leverage that, right? So KEDA is going to implement all of the intelligence into, and register that into the external API, and HPA will just base the scaling on that, right? But we're going to see in the demo. So it's all I said. It acts as a metric server. So think about KEDA really as a proxy, intelligent proxy for HPA to operate. So you define a scaled object in Kubernetes, and that CRD will essentially influence and automate HPA custom resource. So it's the combination of both. It's really automation. We have the super chef, the proxy, which is the scale object, and we have the dumb chef, which is the HPA object inside Kubernetes. Right, so here we have an example. It's Kafka. In the demo, we're going to do use NAT. So here you can see the scale target reference, which is the name of the object to be auto-scaled. So here a Kafka consumer. You give the trigger, and then the metadata is going to be all the parameters for the metrics to be able to be gathered by KEDA. So here we need the address of Kafka, the consumer group, and topic. And then because we expose directly this into the metrics, HPA can directly access that without having to use a Prometheus adapter that you have to customly deploy for if you were using HPA only. Okay. All right, this is a bit of anti-patterns. Essentially, I've already mentioned this. If you set CPU limits equal request, the risk is that you're going to have performance throttle before HPA can scale. HPA with low requests, then we can trigger too easily because it's a percentage of that request. HPA and VPA on the same workload but on the same resource, CPU memory, doesn't work. You can use same workload but different metrics that work. Not using PDB with VPA, it's bad, so always use PDB. to make sure that, especially if it's a stateful workload, so that you don't run into this issue where you don't have enough workloads for serving your application. And priority class. Priority class is very important, especially if you don't set limits, because those workloads, again, instead of being guaranteed, they fall into those particular burstable class. Okay, let's go for the demo. So again, if you have a laptop, it's the moment to use it, or your phone. So if you can scan that, or just use the URL, it's ngrok, so it's running on my laptop. So the idea, it's a meme generator with a front end. That front end is, I'm just gonna wait for a couple of seconds. How much time do I have? 10 minutes? 10 minutes, so probably no questions. All right, so the idea is to make the environment scale by using a meme generator. So it's a, let's say we have multiple components. So we have the front end, the React front end that you see on your device that is requesting when you enter, whatever prompt in the application is going to send a meme request on the NATs. So we have a dedicated subject for that, so meme request. So from the NATs TypeScript code, we send a request to the meme request subject into, I'm using Jetstream for NATs because it's persistent and actually support WebSocket. So we have a WebSocket connecting to the stream. Then we have a backend written in Rust that is going to process that particular meme request, so subscribing to that particular subject. And then we have a Redis cache that is going to cache all the different memes that are rendered. And the goal of the backend in Rust is to process the meme request using the Hugging Face inference API, using Flux text-to-image. And once Rust is managing that request, it's going to reply back to another subject that is meme response, and then it's going to be displayed into the front end. So we have different things to scale. First, we have the front end, but the front end is behind an ingress controller. So actually, we're going to scale not the front end, but the ingress controller, because this is the one that's going to handle all the requests from the front end. Then we want to scale the backend based on the number of pending messages into the Jetstream stream. And finally, we're going to scale vertically the Redis cache based on the number of memes that are going to be cached. Right? So let's move to that. And if you don't manage to do it, which probably I don't think there's enough people, but we'll see. I have a bunch of script. But let's go to this whole idea of, so hopefully everyone now kind of have this image of the application. We have the front end, we have the message bus, we have Rust, and we have Redis, and we have the API. So here the application is deployed. Actually, there's already a front end, so probably you've generated already. That's good. I didn't expect that. I thought the ingress would be scaled first. Well, that's good. So we already have the HPA. So HPA definition, so just to show you, we have the namespace meme generator here. So this is our front end. Now we have 2, 4, 6 replicas. And they have just been, because you were guys using it, it's scaled from 1 to that number. And we have the backend. So the backend is just 1. If we check at what we have in terms of HPA configuration, this is the front-end configuration. If you go into the YAML version, if we go to the definition, so we have here target usage. Average utilization is 30% for the CPU, 50% for memory. And here I've got some policies that have been applied. So the period second when it's going to monitor before scaling down. And we have the same thing for the scale up. And the value is how much. So 100% means that, for example, here, you will scale up by 100% of the current number of pods. So if I have 5 pods, if I put 100% there, next time it's going to scale, it's going to be 10 pods, right? Scale down, same sort of principle. 50% means that after 60% of where I'm going to be watching that's how much it's used, then 50% is going to mean that you can reduce the number of replicas by not more than 50% of the running replicas. So if you have 10, it's going to reduce it by 50%, so only by 5, right? So that's for HPA. So if we take a look at the VPA configuration, here the ID, 5 minutes, okay. I've put it on auto, but because I have a stateful set, it's not going to restart the pod for me. So this is my VPA configuration, so minimum allowed, so it won't recommend anything below that. Maximum allowed, it's not going to recommend anything above that, and it's going to monitor both CPU and memory. So this is for Redis. So if I look into Redis right now, if I go to pods, Redis, if I go into YAML, and then if I check the resources, so it's the one I've done at the beginning from when I deployed the application. Request 100 mil for CPU, 512 for memory. So now what I can do for my pod, Redis, I can go into, I need to run my Redis, so that will be Redis 6379, and now I can probably run something like Redis cache, benchmark. So I'm going to stress Redis for memory. So Redis is memory bound. So here what I want to do is, oh, did I deploy the VPA? I'm not even sure. Let's try to do this. VPA, I don't have the vertical pod autoscaler. So let's deploy this. So we're going to do kubectl apply, not this one. So apply, that's Redis and VPA. Here you go, VPA. If I just check the YAML, 3 minutes, my God. Okay, we have to go fast. Let's run that. So hopefully we should see CPU and memory appear here. Yeah, so this is now the recommended values, right? And now what I can do is just restart Redis because it's a stateful set. I'm just going to restart it. And I should see the container popping again with the appropriate. Now if I go to resources, again, right? I can see that the memory request has changed, so job done. So we've done VPA. I mean, VPA worked for the front end, so I won't show you for the ingress. Now the last part is the message bus. So remember, we have this namespace meme generator. So I want to scale the meme generator backend, which is that one, by stressing NATs. So I'm going to send a lot of requests using the Hugging Face. And normally, if I check also, it's going to be here. I've got all the Grafana dashboard coming from my Rust backend. It's going to spike, you can see here. So not that much Hugging Face, so I should have like a lot of more 1,000. Okay, still $0. I don't want to kind of stress it too much, but I've got room for that. Okay, so you can see now the KEDA, the scale object. I'm just going to show you very quickly. Scale object is defined here. It's active, and how I've configured it is basically it's going to monitor that particular external metrics. So remember what I said at the beginning, KEDA is this kind of proxy. So KEDA is going to tell HPA, monitor that external metrics that I've implemented for you. And if I go into, 1 minute, if I go into HPA now, I will see the backend scaler programmed by KEDA, and if I look into it, I will see that here, the metrics it's using is the one provided by KEDA, without having me to create a manual, adapter using Prometheus. And because it was quite on purpose, I make it quite aggressive in terms of the metrics. Now that I've served all those messages, I have 0 message in the queue, so it's scaling back to the minimum, which is 1, but I could also have made it 0, but then with 0, there's always a bit of, especially because it's a Rust backend, a little bit of, cold start, which I didn't want to happen. It worked. I was a bit fast. All right, so I think we are over. So just if we want to remind something and get something out of that particular talk, use VPA to scale memory. Use KEDA HPA for CPU scaling. Use KEDA if you want to be smart and not scale based on CPU and memory. Set requests and limits for memory. Set requests for CPU with no limits. If you do that, remember of the priority class, because it's then is moving into this burstable instead of guaranteed quality of service. If you need scaling to 0, again, KEDA is a good solution for that. And the final thing is really use VPA, at least by default, without doing nothing, in initial mode, so at least you have the right profiling for your application. And I think that's me done. All right. I think we're out of that. Thank you.